So today we have to study the variation of resistance in a material with temperature. When we heat the body, when temperature of the conductor is increased, what happened to resistance? Okay. So while explaining Ohm's law, I told you when temperature is kept constant, V by I is equal to a constant. V by I is giving the resistance. If temperature is varied, what is happening? Let us see that. When temperature is varied, okay, what will happen to resistance? Resistance is constant when temperature is kept constant. V by I is a constant. When temperature is varied, we can see what all things happens. So you can watch this. These are the ions, and in atoms or lattice points. This white color, that is atoms. And you know the small ones, that are the electrons in the atoms. Red balls. Electrons in the atom. Free electrons. And these are atoms or lattice points, or ions, you can tell. Atoms or ions. Positive ions. Electrons are revolving around them. And in a good conductor, there are large number of free electrons. And when we apply potential difference, an electric field is set up, positive to negative, and electron begin to move towards the positive terminal of the battery, opposite to the electric field. Okay, and let us see what is happening when temperature increases. So you watch this, and I'll ask question.
These free electrons are responsible for the flow of electric current across the conductor. When we apply an external electric field, this electron begins moving in between the lattice points opposite to the direction of the applied electric field. Each electron pushing the other by force of repulsion. At normal or low temperature, these atoms or lattice points are at fixed position, so the electrons can move easily between these atoms. But when we increase the temperature of the conductor, these atoms starts vibrating, and this vibration of atoms provides hurdles and resistance to the flow of electrons or holes. So with the increase of temperature, the lattice or atomic vibration increases by gaining the thermal energy. Because of this increase in the vibration of atoms, the resistance of the conductor increases. Thank you for watching, and don't by gaining the thermal energy.
Okay, children. See, when temperature is increased, what we have seen? The Bangsha, what we have seen when temperature is increased, whether you observed it. When temperature is increased, what happened? Whether you understood it or
ഹലോ
not.
മാം ടീച്ചർ ഒരു പ്രാവശ്യം കൂടെ എക്സ്പ്ലെയിൻ ചെയ്യോ ഇവിടെ വോയിസ് ബ്രേക്ക് ഉണ്ട്
ആണോ? അപ്പൊ ഞാൻ വേറെ ആരെങ്കിലോട് ചോദിച്ചു നോക്കട്ടെ, കിട്ടുമെന്നറിയാലോ. ഓക്കെ. Adil Krishna, have you observed this video? Adil Krishna? മിണ്ടൂല. Muhammad Adil?
Teacher.
Have you observed this video?
Sound ഇല്ല ടീച്ചർ, സൗണ്ട് ചെറുതാ, കേൾക്കാൻ പറ്റുന്നു.
സൗണ്ട് ഇല്ല. പിക്ചർ കാണുന്നുള്ളൂ അല്ലേ? എല്ലാവർക്കും അങ്ങനെയാണോ? സൗണ്ട് കുറവാണോ എല്ലാവർക്കും? അല്ല അല്ലേ? അപ്പൊ മുഹമ്മദ് ആദിലിന് മാത്രമാണോ ലോ ആയിട്ട് കേട്ടത്? മറ്റുള്ളവരൊക്കെ ശരിക്കും കേട്ടോ? ഓക്കെ. അപ്പൊ എന്താ മൈക്കിനോ നെറ്റിനോ എന്തെങ്കിലും പ്രശ്നമായിരിക്കും. ശരി, അപ്പൊ ടീച്ചർ പറയാം. അപ്പൊ ശ്രദ്ധിച്ച് കേക്ക് കേട്ടോ. ഓക്കെ, ടീച്ചർ പറയാം. ഓക്കെ, ഇനി പറഞ്ഞ് കേട്ടവരോട് ചോദിച്ചോക്കട്ടെ. Okay, Sagar, have you heard voice? Seen this video, Sagar? ഇല്ല. ശ്രീരാഗ്, ശ്രീരാഗ എവിടെ പോയി? ഉണ്ടല്ലോ. Jnanaprakash and I think Jnanaprakash heard.
Ma'am, resistance increases while increasing temperature.
Resistance increases when temperature increases. Resistance increases. What is the reason? That is what I am asking. What is the reason?
The vibrations of these ions increases.
Vibrations of atoms or ions increases, and due to that, what happened? It begins to move. It begins to vibrate. So what happened to the motion of electrons? Temperature increases, vibration of the atom itself is taking place. So what happened to the motion? You just observe. It was
Because of this increase in the vibration of atoms, the resistance of the conductor increases. The increase in the vibration of atoms, the resistance of the conductor.
when it vibrates, it is colliding. Understand? The electrons begin to collide more frequently. That is the reason. Clear? Jnanaprakasham?
Yes, ma'am.
So when temperature increases, the resistance increases because
due to collision between ions.
Increases. That you tell. Collision is already there. Collision is already there. But when temperature increases, what happens?
Resistance increases.
Collision becomes. Anyone, please complete. Collision is already there, and it is that it offers some resistance to the motion of charges. But when temperature increases, the ions begin to vibrate more vibration. Earlier, that vibration was not there. When temperature increases, this white color, that ions begin to vibrate. So what happened to this motion of the electron? They are obstructed due to the vibration. They collide. Anyone, please complete. ഇത്രയും പേര് നോക്കിയിരുന്നിട്ട് എന്താണ് സംഭവിച്ചത് മനസ്സിലായില്ല. കൊളിഷൻ എന്ത് സംഭവിച്ചു? കൊളൈഡ്
with ions.
കൊളൈഡ് അപ്പൊ മോർ ഫ്രീക്വന്റ്ലി ആ വേർഡാണ് അവിടെ ഉപയോഗിക്കേണ്ടത്. കൊളൈഡ് മോർ ഫ്രീക്വന്റ്ലി. സോ ആവറേജ് റിലാക്സേഷൻ ടൈം മോർ ഫ്രീക്വന്റ്. പെട്ടെന്ന് കൊളൈഡ് ചെയ്താൽ ടൈമിന് എന്ത് സംഭവിക്കും? ഇൻക്രീസ് ചെയ്യോ ടൈം? പെട്ടെന്ന് കൊളൈഡ് ചെയ്യാന്ന് പറഞ്ഞാൽ ടൈം ഇൻക്രീസ് ആണോ ഡിക്രീസ് ആണോ? ടൈം ഡിക്രീസ് ആണ് ചെയ്യുന്നത് അല്ലെ? ഡിക്രീസ്. റിലാക്സേഷൻ ടൈം ഡിക്രീസസ്. അപ്പൊ റോ ഈക്വൽ ടു m/n² ടോ ഇൻ ദ ഡിനോമിനേറ്റർ ആണ്. റിലാക്സേഷൻ ടൈം കുറഞ്ഞു. അപ്പൊ റെസിസ്റ്റൻസ് അല്ലെങ്കിൽ റെസിസ്റ്റിവിറ്റി കൂടി. റെസിസ്റ്റൻസ് കൂടിയാൽ റെസിസ്റ്റിവിറ്റിയും കൂടും. രണ്ടും ഒരേപോലെയാണ് വേരി ചെയ്യുന്നത്. റെസിസ്റ്റൻസ് കൂടിയാൽ റെസിസ്റ്റിവിറ്റി കൂടും. അപ്പോൾ so what we have seen here, when temperature is increased, the ions begin to vibrate and the collision becomes more frequent. Average relaxation time decreases and thereby the resistance and resistivity increases. That happens in the case of a conductor. But insulator, semiconductors, its behavior is different. In conductors or metals, this is happening. Okay? So when temperature increases, what happened to this resistance? Akshaya?
Increases.
Resistance increases in conductors. Okay, what is the reason? When
we increase the temperature, the ions start vibrating frequently and it disturbs the movement of electrons.
Yes. So collision, relaxation time
decreases.
Therefore, resistivity and resistance
increases.
Very good. Increases. Okay. So that is happening here. I think it is clear now. Boys ഒന്നും മിണ്ടറില്ല. ജ്ഞാനപ്രകാശം എല്ലാം മിണ്ടുണ്ട്. ദീപാംശ കേട്ടോ ഞാൻ പറഞ്ഞത്? ദീപാംശ?
Yes, ma'am.
So when temperature increases, what happened to resistance of a conductor?
It also increases.
What is the reason for this increase?
It collide with the ions
More frequently. That word you have to use. And thereby relaxation time
decreases
and resistance
increases.
Resistivity and resistance increase. Very good. ശ്രദ്ധിച്ചിരിക്കണം ക്ലാസ് കേട്ടോ. ഓക്കെ ഓക്കെ അപ്പോൾ then I will show you other video. And graph is there variation. I'll show a graph. One, we have to plot a graph between resistance or resistivity with the temperature. Oh, that is gone. Okay, I will show you later. Okay, I will show you later. Not required. This is a very important point in the resistance variation with temperature. Only 30 children are today present. Temperature dependence of resistivity. Effect of temperature on resistance. Let R1 be the resistance of the conductor at temperature T1. Initially, resistance is R1 and it is heated to a temperature T2 and resistance is found to increase in the case of conductor. Okay, conductor resistance increase. So increase in resistance is R2 minus R1. This I think I have explained last class. Temperature coefficient of resistance. Is it, children? Increase in resistance directly proportional to initial resistance. Directly how much to what degree we are increasing the temperature. That also it depends. Resistance increase depends upon the temperature difference and also its initial resistance. And we got R2 minus R1 is equal to some constant alpha into R1 into T2 minus T1. Therefore, alpha is equal to R2 minus R1 by R1 into T2 minus T1. Alpha is known as temperature coefficient of resistance. SI unit is R2 resistance. R2 minus R1 is resistance. R1 is resistance. So its unit will cancel and we get temperature unit alone. T2 minus T1. That is Kelvin. Kelvin raised to minus 1 is the unit of temperature coefficient of resistance. So in metals we can see this R2 is final resistance is more than the initial resistance. So R2 minus R1 is positive. In metals, R2 minus R1 is positive, high positive value, very high increase is there. So R2 minus R1 will be very high value. So alpha, temperature coefficient of resistance is high positive value for metals or good conductors. But you know, in insulators, that very high resistance we can see. There is no insulator, we know it will not allow current to flow through it. Understand? So infinite resistance it is having, high positive value, very high positive value, infinite resistance, insulator of earth. Okay. So here and semiconductors, what happened? Temperature increases, resistance is decreasing. Electrolyte also, when temperature increases, resistance is decreasing, and that means final resistance will be less than the initial resistance. That I will explain what happens. Okay. Temperature coefficient of resistance alpha is highly positive for metals. For insulators and semiconductors, alpha is negative, but for some alloys, manganese, tungsten, eureka, the value of alpha is very small positive value compared to metals. Due to high resistivity and low temperature coefficient of resistance, these alloys are used for making standard resistance coil. I explained, I think, last class. Ohm's law, I showed you one silver colored wire. It is having high resistance, but alpha is very small because it is made of an alloy. Tungsten, manganese, remember these words, these names, children. Alloy, manganese, tungsten, eureka. Such wires are used as standard resistance wires. Why? Because their alpha is very small positive value. That means resistance is not increased much when we increase the temperature. When current is passed, you know, the temperature usually increase, heating effect of electric current. When current is passed through a wire, its temperature increases due to the heating effect of current, and thereby there is possibility of increasing the resistance. But you know that due to the particular material, due to the it is made of an alloy, and its resistance is not increased much. So what happened? Alpha is a very small positive. R2 minus R1 is small, slight increase only, not much. So that value, small positive value for this material, manganese, tungsten, and eureka. That's why they are used for making standard resistance coil, standard resistance wires. They are used, these alloys are used. Very important point, this one. Temperature dependence on resistivity. So resistance variation and resistivity variation are similar. If you study resistance variation, that is the same as the resistivity variations, children. So it's easy to remember things. Resistance and resistivity vary in a similar manner. The resistivity of a metallic conductor is given by rho equal to m by ne square tau. We have studied this relation. Resistivity rho equal to m by ne square tau. What is m, children? What is m? Arila? Mass of the electron in the conductor. E, charge of the electron in the conductor. N, density of electron, number of electrons per unit volume in the conductor. Tau, average relaxation time. What is relaxation time? Time between two successive collisions. Time between two successive collisions. When temperature increases, we have seen that relaxation time is decreasing. Tau decreases. So resistivity. Mitra, what happened resistivity when tau decreases? Mitra is there? Abhinav, what happened when temperature decreases? Temperature increases, relaxation time. Abhinav. Adilakshmi.
Yes, teacher.
When temperature increases, relaxation time
Decreases.
Resistivity
Decreases.
അതെങ്ങനെയാണ് ഡിനോമിനേറ്ററിലല്ലേ എടുക്കണേ ദിസ് ടോ ഡിക്രീസ് ചെയ്യുമ്പോൾ ഇതിനെന്താ സംഭവിക്കുക ടോ ഡിക്രീസ് ചെയ്യുമ്പോൾ റെസിസ്റ്റിവിറ്റി what will happen? Increase അല്ലേ My
increases.
So tau decreases, resistivity increases. Okay. So when temperature increases, resistivity is increasing. Okay. For a given conductor, rho is inversely proportional to T, tau, relaxation time. As the temperature of metallic conductor is increased, the ions and atoms vibrate with the higher frequency or amplitude about their mean persistence. Due to increase in the frequency, the number of collision increases, relaxation time decreases, hence the resistivity of metallic conductors increases with increase in temperature. That we have seen in that video. Okay. For most of the metals are good conductors. Resistivity increases with temperature. So all the metals, resistivity, resistance, both increases linearly with temperature. When you plot a graph, we get a straight line graph, temperature and resistivity graph. That is a straight line graph for metals. Linear variation we can see. Linearly with temperature around and above temperature. Such cases, the equation is this. Rho T, that means resistivity at a higher temperature is equal to rho 0. This is at 0 degree Celsius. 1 plus alpha bar into T minus T0. Alpha bar means temperature coefficient of resistivity. At T temperature, resistivity is rho T. At T0 temperature, resistivity is rho 0. This is the relation connecting. Resistance also we have some relation. RT equal to R0 into 1 plus alpha T minus T0. We have got same relation, similar relation for resistance. So if you study one relation, the other one. See, that equation we have seen R2 minus R1 by R1 into T2 minus T1. Same thing. R2 minus R1 by R1 into T2 minus T1. Instead of that, we have taken rho T minus rho 0. R2 minus R1. R1 initial, R2 final. Rho T is final, rho 0 is initial resistivity. The only difference in letters. The other thing, equation is same, variation is linear. So you have to study both the formulas. Alpha equal to RT minus R0 by R0 into T minus T0 or alpha bar. Alpha bar means what? Temperature coefficient of resistivity. Alpha means what? Temperature coefficient of resistance. So in order to understand the difference, we put a bar here. Not the difference. Here we write rho, there we write R. That's the only difference. So rho T minus rho 0 by rho 0 into T minus T0. What is T here? Final temperature. What is T0? Initial temperature. What is rho T? Final resistivity. What is rho 0? Initial resistivity. So that equation, we can define temperature coefficient of resistivity. How will you define this? Temperature coefficient of resistivity, how will you define? You have to make, see, it is the difference in resistivity per unit original resistivity per degree Celsius rise in temperature. So when this is made 1, rho 0 is made 1, unity. When temperature difference is made 1, for 1 degree Celsius, we are finding the resistivity change. 1 degree Celsius. Initially, it is having that unit original resistivity. For, see, rho 0 is made unity. T minus T0 is also made unity. Then alpha bar is the change in resistivity. Initial final resistivity minus initial resistivity. That is the change in resistivity. So this alpha bar is equal to the change in resistivity when rho 0 is 1, T minus T0 is 1. That means unit original resistivity per unit degree rise in temperature. So alpha bar, temperature coefficient of resistivity, is the change in resistivity when rho 0 is 1 and T minus T0 is also 1. Okay, that is the definition for alpha bar. Okay, Alpha bar is positive for metal, just like alpha, the same property, positive for metals, small positive for alloys, negative for insulators and semiconductors, same behavior. And this graph is also very important. Just by giving the graph, you will be able to identify the material. Okay. Temperature, see, temperature and resistivity graph. Temperature in Kelvin is given. Resistivity into 10 raised to minus 8 ohm meter, it is given. 0.2, 0.4, 0.6 into 10 raised to minus 8 ohm meter. This is the graph between temperature in Kelvin and the resistivity of the metal. What can you say about this graph? Is the resistivity increasing with temperature, children, in this graph? Just by looking the graph, tell, yes. See, you can see the rise. As the temperature increases, the resistivity is also increasing. Understand? But here you can see it start only after a while, that resistivity. Initially at zero temperature, 0 Kelvin temperature, it is having some resistivity. Even at 0 Kelvin, it is having some resistivity. Then only it starts increasing. Understand? Even at 0 Kelvin, it is having some resistivity. And when we heat the material, resistivity is increased. So, when resistivity increases, conductivity
Decreases.
decreases. Very good. Conductivity decreases. Okay. So, this is the graph for copper. Just so you will be given the graph and you will be asked to identify the material. So, just by looking the graph, you should be able to tell this is not linear. Initially, it is a curve, you can see. Later only, we can see the linear increase. Initially, it is a curve. So just by looking the graph, you should be able to identify the material. This is the copper, chloride copper. This is the graph, temperature, resistivity graph. And nichrome, you see, nichrome, even at 0 Kelvin, it is having a high resistivity, not like this. This is 0.2. So this will be very, very small resistivity. But here, nichrome material, even at 0 Kelvin, it is having a high resistivity. Then its variation is linear, not the curve. Variation is linear. Okay, increases. Resistivity increases with temperature, and it is linear also. Okay, nichrome. Then semiconductors variation is different. I told you in semiconductors, resistance and resistivity decreases with temperature. Let us see how that happens. Metals we have seen, relaxation time decreases, and thereby resistivity increases. But in semiconductors, what is happening? Let us see. We know the formula, rho equal to m by n square t. This can be used in both cases. Rho equal to m by n square t. In metals, we have seen tau decreases, rho increases. But here, when tau decreases, one thing is increasing. That is n, number density of the free electron is increasing. That is happening. You will study semiconductor in detail later. One full chapter is there on semiconductors. There you will study in detail. Now, as we are studying the resistivity of different material, we have to study this here also. So, based on our equation that we have studied now. And here you see, in semiconductors, when temperature is increased, we know relaxation time decreases. That's okay. Same thing happens here. But one more thing is happening here. Number density of electron is increased. That is the difference. There, not free electrons are available in conductors. No, there is no much increase in the number density of electron. But semiconductors, free electrons are less. Semi only. Conductivity is semi. Free electrons were less. But when temperature increase, all the bond break and large number of electrons were produced. Children, in semiconductors, when temperature is increased, relaxation time decreases. So both conductors and semiconductors, that happens. Relaxation time decreases. But in this particular material, semiconductor, N is increasing with large amount. When we increase the temperature, the bonds break, covalent bond break, large number of electrons are produced. So that is prominent here. That is prominent. So increase in resistivity is more than the decrease in relaxation time. This compensates more. This effect is more prominent. So what happened? An increase. What happened to resistivity? And number density of electron decrease. Decrease. That is happening here. And increases, rho decreases. That is happening here. That is happening here. Okay. And number density n increases, but relaxation time decreases. That is as usual. But increase in n compensates more than the decrease in tau. Due to it, for semiconductor, rho decreases with temperature. So very important thing. And graph also, I'll ask question, which this graph is for which material? Semiconductor one graph is there. See. This is the variation of resistivity with temperature in semiconductor. Just by seeing the graph, you will be able to tell the material. See, you can see a curve. When temperature is increased, resistivity, initially high resistivity. When we increase the temperature, resistivity is found to decrease. The resistivity is found to decrease. So, which material is that? This is semiconductor. And electrolyte also the same behavior. Resistivity of electrolyte also decreases with rise in temperature. That is the reason is also written in electrolyte. What happens? The reason is that with a rise in temperature, viscosity of electrolyte decreases, so that ions get more freedom inside the electrolyte, hence resistivity collision take place and resistivity decreases. Understand? Ions will vibrate more, and because of that resistivity decreases. That is happening. So this curve is for which one, children? This curve, resistivity decreases with temperature. Which one? Semiconductors and electrolyte. Okay. Then series resistance combination, you have to study the formula only. When resistance are connected in series, what is the effective resistance? Rs equal to?
R1 plus
R1 plus R2
plus R3. Okay. Resistance are connected in parallel. What is the resistance?
1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3.
Very good. So that you are knowing, and you have to use all those formulas to do the problems. EMF and potential differences I have explained. And internal resistance of a cell. What is the reason for internal resistance? It is due to the nature of the electrolyte, and it is due to the nature of the electrodes, distance between the electrodes, and inversely proportional to area of the electrode. Okay, all those things we have seen. Cell also explained, and this one is there to explain. Today only 31 students are. Okay. I'll explain this. Already explained, but with another figure I explain. But not one figure is given. I will have to explain that also. Then only you can study. Okay. Relation between internal resistance, EMF, and different circuit, that case will be different. If no resistance, you have no need to consider capital R. When there is an external resistor, you have to consider that one. Current will be different. So depending upon this situation, I have to explain these formulas. Relation between internal resistance, EMF, and terminal potential difference of a cell. Here you can see a cell, battery, and it is having an internal resistance. I told you every cell is having some internal resistance, opposition to the flow of current. Flow of charges inside the cell. Internal resistance is usually we represent with small letter r. Small letter r, we represent internal resistance of the cell. We are not representing inside, just near to that we represent the internal resistance. Near to the cell, we represent one small letter R, that is the internal resistance of the cell. But capital R, you know, a resistance wire, just like Ohm's law, I showed you one wire, no? It's having tungsten or manganese. Such wires are having high resistance. That wire is connected here. Resistance wire. But this wire we connecting wires. So what all things you can see? This is a very simple circuit. Very simple circuit. Big circuit are coming, children. This is very simple circuit. What all things you can see in the circuit? Please tell. Symbols you should know. When you see the symbol, you should know what is it. R. What is R, children? What is R? Resistance. It may be made of. Then constant then manganese, such material, okay, which is having very high resistance, low value of temperature coefficient of resistance. Low value of temperature coefficient of resistance. That means by increasing, please Akshaya, mute your mic. By increasing the temperature, resistance is not changed much. Such a material we use here, standard resistance wires. So R is one such material, and then you can use connecting wires to connect it to a battery. Battery is connected. Then what this small r represent, children? Small r.
Internal resistance
Of the battery. Internal resistance of the battery. And here you can see a key also. Once I explained Ohm's law, I showed key. When you keep that plug inside this gap, what happened? It becomes closed. And current begins to flow. This is the source of EMF. E is the source of EMF, and we know the charges begin to flow when a potential difference. This is the source of EMF. See, when we connect a battery here, this end of the resistance becomes positive and this end of the resistance becomes negative. When electric field is set up, electrons begin to flow opposite to the direction of the electric field, and thereby a current is produced in this resistor. And when current flow through the resistor, according to Ohm's law, potential difference is developed. What is V? What is the potential difference developed across the resistor according to Ohm's law? V equal to IR. V equal to IR. That is the potential difference developed across this resistor. So potential, that is the terminal potential difference. When current is drawn from the cell, what potential it shows? That will be same as the potential developed across this resistor. You just connect a voltmeter here. Now other resistances are there. Okay, this is the internal resistance. So whatever terminal potential difference is there, V, for example, I told you when current is drawn from the cell, V equal to E minus IR, I into small r. That we have seen one class. And here, so terminal potential difference across this resistance, that is always less than E, because V equal to E minus, children, complete it.
Internal resistance.
E minus IR.
IR.
I into small r, okay? I into small r, okay. Then now we are having two resistances. Even though it is the internal resistance, it is offering resistance to the flow of current. So total resistance in the circuit, can you tell what? They are in series. This small r and capital R in series. What is the total resistance in the circuit?
R plus small r.
Very good. R plus small r is the total resistance.